Okay, hello everyone. Welcome to this session. So today I'm going to talk about empowering GPU acceleration for Java. Exciting, isn't it? So I'm going to start by explaining why we are doing what we are doing. So as you all know, Java is very well positioned when it comes to server applications, cloud applications, and enterprise applications. And one of the main reasons is this mantra, this philosophy of writing once, running everywhere. But when it comes to accelerators, right, the situation is a bit different, right? Java is usually off limits, forcing developers to use native libraries or to use different programming models, like a Java programming model environment and the native programming environment. So there are ways to lift up this. In fact, there are projects out there. We want to talk about those projects very briefly during the presentation. But in a nutshell, with the advent of the project Panama, along with the project Babylon with core reflection, allow us to target foreign programming models in a much way easier manner. And that's the topic of this talk. So I'm Juan, by the way. I'm a software engineer at the Oracle Java Platform Group, working in the Java core libraries team. So today I'm gonna talk, first of all, a brief description about core reflection, introduction to core reflection. It's gonna be like intro to core reflection in 3 minutes, right? I assume that many of you were in the previous talks by my colleague Ruby and Paul talking about core reflection in depth. So this is just a recap about setting up the terminology I need for the rest of the presentation. And then I'm gonna dive into the HAT, the GPU part. I'm gonna explain the programming model. I'm gonna show you some examples. I'm gonna show you how you can run it, etc. And then I'm gonna show you 2 case studies. One showing the cost of data extraction when it comes to GPUs from the Java side using HAT. And the second case study is how far can we go with this technology? And I have some comparisons against native. So let's get started. Core reflection and Babylon. So what is Babylon? Babylon introduces mainly 2 things, right? The first of all is an API, okay, a core reflection API that facilitates Java programmers to create a symbolic representation of the Java code, Java methods, and Java lambdas. That symbolic representation is what we call a code model. With this code model, what you could do is to analyze it, you can manipulate the code model, you can transform it to something else, or you can generate code for heterogeneous programming environment, for example, for a GPU. Let me show you an example of core reflection. Well, and the second part of the second component of Babylon project is this HAT, the backend for GPUs, right? So I'm gonna show you now an example of using core reflection. So we have a Java method called compute, very simple one. We have 3 parameters, A, B, and C, and some computation in the method body. The first thing to notice is that the method is annotated with this @reflect annotation. This instructs the Java C compiler to generate a code model for this method. And that code model will be stored in the class file, right? Then at runtime, we can query that code model from the class file and do something with it. We can analyze it, we can, as I said before, manipulate, transform it, etc. So let me show you the code model that corresponds to this method. It looks like follows. So if this is the first time you see a code model, it looks like very intimidating, but it's actually pretty easy. Let me show you the main parts here. So we have a function called compute that matches the name of the method, right? And then we have the list of parameters 0, 1, and 2 that matches A, B, and C. Each item, each element in this tree has a unique ID. It's kind of close to an SSA representation, if you like. Then we have the bar declarations, so we can see actually the names A, B, and C. And then in between we have the actual operations. We have the multiplication and the addition, right? And in between we have the loads that correspond for each operation. So this is how the code model looks like, but the interesting part and the fun part is when we can transform this code model. For example, we could do this multiplication and addition, do a transformation and say, this is an FMA operation, right? So we can create a new operation, transform the code model, and create a new code model with this tiny optimization, right? And this is the key thing when it comes to HAT and the GPUs. We use this strategy all the time in HAT to transform the code to our needs, to match the programming model under the hood, like the CUDA programming model or the OpenCL programming model, etc. This is an example that you can find in the Babylon repo, by the way, and there's a section there as an example suite, and it's very well explained, so you can debug your example. It's very nice because you can integrate it with your IDE and see what's going on step by step. Right, so what else can you do with code reflection? I show you a very, very simple example just to illustrate the purpose, right? But with code reflection, you can do many things. Paul, for example, has written some articles about how to have a link-you-like language using code reflection, also to perform automatic differentiation. My colleague Adam, for example, has done a Onyx runtime, a connection with an Onyx runtime. And of course, you can do a GPU front end. So these just are a few examples. Hopefully you get inspiration from this to do what you want to do, right? So if you are interested in diving into these topics, there are a few sessions in the conference here. Adam later on will explain the Onyx runtime, and Liz and Anna will explain kind of everything in more detail. So, code reflection now is preparing for incubation, is under submission now. I put in draft mode, it's under submission. And yeah, it's public, you can read it, you can talk to us if you want. The way to get involved is through the mailing list. As I mentioned, there is an example suite that is very easy to get started with code reflection. Yeah. So let's jump to the GPU side of things. Let's jump to the fun part. So why do we want to support GPUs in the first place? Well, the GPU case is an ideal case for code reflection. We want to try how good is code reflection to support heterogeneous programming models, right? The second point here is that we have another opportunity after the project Sumatra to revisit again how we can enable acceleration for Java using, in this case, code reflection and Project Panama. Because it will be nice in the future to target specialized workloads from the Java side. The star use case these days is AI and LLMs, but there are many, HPC, simulations, embodied simulations, physics simulations, big data, etc. So GPUs are actually used for more than just LLMs, okay? But now, how do we program or how we accelerate from Java? We are not trying to reinvent the wheel here. There are a few projects, I mentioned a few of them here. For example, Project Sumatra was an Oracle project, Aparapi, an attempt by AMD, for example. IBM also has a port called IBM GenI for GPUs, for NVIDIA. Even NVIDIA has its own called Javi, right? It's more like a research project. Perhaps the most famous one these days is Tornado VM. From my experience, all of these, what they have been focused on is mainly on a single kernel acceleration, right? As a kernel in isolation. Tornado VM did a step forward, let's say. What they did was to analyze not just a single kernel, but the ability to have all these kernels in a compilation graph, in a compute graph, and have a wider scope of analysis and execution. And that's very interesting. But many of these projects still, they have a very nice abstractions on top of it, on top of Java, and on top of the GPU programming models. But they might be leaving some performance on the table, right? Just because they're creating these abstractions on top. In HAT, we are taking a different approach. And we think about this because just running faster than Java for some domains might not be enough, right? For many applications, just because you're running on a GPU, that gives you a very good speed up if you write the right application with the right input size, etc. But there are some domains, like for example LLMs and AI, that just running a bit faster is not enough. People, what they want is to be really fast as native if possible. So as I mentioned, HAT, what we're doing is take a step further and learn from all these projects in the past and try to do the extra mile. Hopefully, by the end of the presentation, I can convince you that's the work we're doing here. Okay, so let me go a step back, and I'm going to discuss how a Java program could be executed on accelerators, on GPUs, right? During this process, I'm going to highlight many challenges, but I'm mainly interested in, okay, I have my Java application, how can I map it? How can I run it on a hardware accelerator? Just to be clear here, what we're trying to do is to offload Java code, because there could be another approach that is just calling pre-built binaries, right? Or a library that has really optimized functions. So what we're trying to do is to offload Java code to run on hardware accelerators. So this diagram, I split it into two parts, the left side and the right-hand side, and I go from high level to low level. So it's kind of the compilation and execution workflow from left to right. So on the left side, I represent a Java program, and not the whole Java program, quite likely, is suitable for hardware acceleration, for example, for GPUs. Quite likely, you're going to have some sequential parts and maybe some sections that you want to really offload, right? Those sections are passed to what we call an engine, and the engine is the head of this, is the most important piece here. It will take these potential parallel workloads and will transform this code, this Java code, and will optimize it, and will do the final compilation for to the accelerator we're targeting. But it's more than that. In my experience working on this area, especially when it comes to managed runtime systems like Java, just offloading and running the kernels is not enough to guarantee performance. What you want to guarantee is also to have a good orchestration of code and data. And that's why the engine becomes the most important piece here. Meaning that apart from compilation, we need to handle data properly, we need to send the data, just the data you need to handle execution properly, and so on. So the engine, let's say you have a discrete GPU, so we'll offload from the Java side to, let's say, CUDA code to run on NVIDIA GPU. And then you need an extra step to transform from CUDA to the actual binary. And this is work that is done by the driver, the GPU driver. What we usually do here is to target what is called source to source. So from Java to OpenCL, from Java to CUDA, from Java to even SPIRV, right? You still need a driver to do the final compilation step. So the engine needs to communicate efficiently with the driver as well, right? So you start, think about all this complexity and making all these pieces talk together efficiently. So I'm gonna highlight, in this picture, I'm gonna highlight some of the challenges in doing so. So on the left-hand side, from the Java side, well, how do we express parallelization in a language like Java that was not designed for GPUs in mind when it was designed? So this is a challenge here. The second question is, well, once you identify how do you transform Java code, how we optimize Java code, how do you orchestrate the execution efficiently? And the last piece is, well, how do we deal with multiple vendors? So we don't want to be vendor lock-in, so just running on NVIDIA platform or just running on AMD. As Java is writing once, running everywhere, we want to keep the same philosophy. So we want to be able to run with high performance, but at the same time be hardware agnostic, right? And we want to deal with different ways to perform efficient code generation for different vendors. So in HAT, we tackle all these challenges in one way or another. So in fact, during the rest of the presentation, I'm gonna jump over all over the place here. So hopefully this gives you a better picture of how Java could run on accelerators. We focus on GPUs, but you can plug in your own the accelerator here. Could be an FPGA, could be a tensor unit here, a tensor processing unit, etc. Could be a RISC-V in the future, a coprocessor, right? So that's why the HAT comes into place here. HAT stands for Heterogeneous Accelerator Toolkit, and essentially it offers a set of APIs for you to be able to run on hardware accelerators. It offers an API for kernel programming. It offers an API for composing multiple kernels, similar to what Tornado VM does, for example. We call it compute graphs. It offers an API for abstracting data, and this is actually a cool thing to have, right? Because in my experience, when you limit the set of types, right, it's hard to get more applications involved, because they are forcing developers to just use your restricted set of types. So having a way to represent user data types, okay, through your interface is what we call an interface. I think it's a huge win here. And then we have HAT offers what is called a pluggable backend abstraction. We have now 2 backends, one for CUDA targeting embedded GPUs, another one for OpenCL, and another one for Java. And you can think, why Java? Java's an accelerator. Well, there are a few reasons for that. The main one, I would say, is to allow debugging. I'm not sure if you have used CUDA or OpenCL or one API in the past and tried to debug your application. It's actually a hard problem. It's actually hard. So having a way to debug the application within your IDE in the Java ecosystem, I think is a huge win here. Second reason is that we could have a Java backend using, for example, Vector API. Our programming model, I will explain how the programming model looks like in a bit. Our programming model matches really nicely with the Java Vector API. And you can plug in your own backend. In fact, we want developers to extend this, for example, for Metal, for XLA, you name it, right? So during the presentation, I'm going to expand on each of these topics. So this is very abstract, okay? This is just an intro to HAT. Okay, so how HAT fits into the JVM ecosystem. Probably if you have seen the Ruby's presentation, she has a similar slide. So on the bottom, we have the hardware, CPU, GPUs, and all the type of accelerators. And then on top of it, we have the JVM. The JVM managing mainly the execution for running on CPUs, right? And then we have the piece of the toolkit, the piece that, this is the plugin, right? The piece that we want people to replace and to extend. And that piece gives us an interface for you to plug in your accelerator, your connection with your driver, the vendor's driver, for example, you know, a TPU driver from Google, etc., and the connection with the Panama native interface. We support mainly off-heap types, right? And hopefully, HAT will offer all these abstractions, all these representation as a part of the toolkit. So ideally, we just extend, no, all this with all this functionality with a new backend, and you get a new supported backend for Java using HAT. And on top of it, we have the set of HAT APIs to express parallelization and to interact with the actual runtime. And that comes for free, the connection with Panama FFM and the core reflection API. And on top of it, it's just your Java program, right? On your HAT application. In fact, I will argue that a Java application is a HAT application that always runs on the CPU. And that's interesting mindset, I think. Because if you want to run on accelerator, you just use the actual HAT APIs. Right, so let's dive into the HAT programming model. And I'm gonna go through the programming model with an example. I'm gonna touch many pieces of the API. We are evolving the API, so many of these components, maybe next month evolve, but the key concepts are here. So I'm gonna start with the hello world for GPUs, which is the vector addition or the vector multiplication in this case. And here it's just a pure Java program, pure Java method, right? What we want to do is to multiply 2 vectors. And I describe it in a way that is easier to transform to HAT. And that means that inputs and outputs, I/O, is passed via parameters. Well, we don't usually return, actually, we don't return any objects in this method. To perform the vector multiplication with just very simple code, we just have a for loop and then do the actual multiplication. But we can refactor this a little bit and make it more GPU friendly at the end of the day, if you like. What we could do is to have the main method, okay, with a for loop, and the for loop invokes another function, another method, just with the computation per iteration. So what we have done is identify a method in isolation with the computation to be done per iteration. And that's key when we go to translate to GPU programming models, because on GPUs what we do in the HAT part, in the HAT programming model, is to express the work to be done per thread. And we usually map a thread to an iteration, right? So this is kind of the abstract representation. So you have the three arrays, and usually, you don't have to, but it's the common way when it comes to GPUs. Usually you assign a thread to each data item of the input set, and each thread is gonna run independently, right? In fact, when it comes to GPUs, you run in blocks, let's say, in lockstep. Right, so when we represent this method in HAT, it looks as follows, right? Again, the method body is represents the work to be done per thread, and the method is annotated with @reflect. Remember that @reflect kicks in the code reflection to generate a code model for it. This is because the HAT runtime and the HAT compiler will take this code model and generate the actual CUDA code or OpenCL code from it. So what do we have in between? Let's start with the types, the parameters. We have an object called kernel context, and this object gives us access to thread information, for example. Give me the thread ID is equivalent to give me the iteration I'm executing in this for my local thread, for example. Through the kernel context, you can access as well the barriers, and you can access thread blocks, you can access global index, you can access local index, etc. If you're familiar with CUDA or you're familiar with OpenCL, this looks very, very similar, or one API. And then we have a type called F32 array. Names can change, but the concept is here to represent a float array. And this float array will be stored off heap using the Panama FFM, right? So what we have done here is it's pretty similar to the sequential code. We pass a kernel context that allow us to access data through the thread indexes that the kernel context offers, and we have inputs and outputs using the HAT types. And in between, we load two elements from array A and from array B using the thread index, and then we store the results, again using the thread index, and we store the actual operation we want to do, the vector multiplication. But we're not done yet, because how many threads are we running, actually? We don't know, right? So we need a way to protect ourselves for accessing illegal accesses here. Okay. Let's say we have an array, we are passing an array of 1,000 elements, but we launch, by mistake or not, 1 million threads. So we need to protect this case. So in GPU programming, what we usually do is to have a condition here that says, if the thread index is less than the input size, do the processing, right? In that case, the guard is given by the programmer. Now, the question that Soren had in the previous talk, but how many threads really you're gonna launch? Well, we do this with an ND range. So the second part of the HAT program involves what we call a compute context. Compute context is another method that is reachable from code reflection, so we annotate it with @reflect. And in this case, previously we have a kernel context, right? Now we have a compute context. And in this case, we define a graph of computation, essentially. In this case, we launch one kernel, but we could launch many kernels. And it's annotated with @reflect, because with code reflection, we can analyze the whole data flow of our application, right? And that's in the previous talk when Ruby talks about analysis of data flow and minimizing data transfer. This is in this block of code. And as ND range, we can express ND range for 1D, 2D, or 3D. This is something that GPUs give us, and it's basically a convenient for the programmer. Usually when you have a 1D data representation like a vector, you launch a 1D grid, right? When you have a matrix type and each of the elements in the matrix can run independently, we map a 2D range, essentially. And the same for a 3D, like a volume. And we can also define partitions. So how threads are partitioned within the global space. And depending on your partition, like the comment that Soran was talking before, depending on your partition, you can have different speedups. I will show you an example later on about this. Okay, and how do we launch this application? Well, the rest is just regular Java code. We have an accelerator object. You attach, for example, I want accelerator for the CUDA backend or for the OpenCL backend. And through the accelerator, you call compute and you pass a lambda. And your lambda is calling the compute that we had before, right? You're invoking your compute graph, right? And that compute graph is reachable for core reflection at this point. And what about the data? Well, through the accelerator, we can allocate the data. HAT exposes a set of types, in this case F32, but HAT also gives you the opportunity to define your own types. More on this later. And each type has a factory method to allocate data with Panama. That data is going to be stored obviously off heap, and it could be stored directly on the accelerator's memory if we want to. For now, it's on the host side still, I mean the CPU side. But if you have a shared memory system, for example, or a discrete GPU, we could store it directly on the GPU memory. Yeah. And how all these pieces fit together? Well, here is the whole example. We have a class, example HAT, and all of these three components that I already explained, right? We have the kernel layer, the compute layer, and the setup to launch the application. Another question is where this code runs, right? Is running with Java and JVM, or is running on the accelerator? Well, let's figure out. So the kernel layer is meant to be executed on the accelerator, on the GPU, for example, right? The kernel code is legal, so it's syntactically Java correct code, but it's not semantically correct. It doesn't have to be semantically correct. In fact, in the case of HAT, it's not semantically correct. We're creating kind of a domain-specific language within Java, okay? To run in Java, you need the HAT runtime that supports this model, right? So this code is never meant to be executed on the Java side unless you are debugging it. It's meant to be offloaded and dispatched to the GPU. The next layer is what we call the compute layer, and this layer will be executed in the Java virtual machine with the Java runtime. It doesn't have to be. There are ways, or there could be reasons to offload this and generate directly native code and run it through a native interface automatically. But for now, HAT dispatches this through the Java runtime. And in this case, we have a restricted set of Java. So it's syntactically correct Java and it's semantically correct Java, but with some restrictions, right? So we don't support, for example, recursion. It's reachable from add reflect. So we have to be careful what we put here in order to be able to communicate with accelerator. And the last piece is what we call the Java application, just to run, to invoke the compute layer, and that's standard Java and runs in the host in the Java virtual machine, right? So hopefully this diagram gives you how all these pieces are connected together and where they are executed. Right, so in HAT, we can also exploit the memory hierarchy of the GPUs. And this is more GPU related, right? So here I show you a very simplified diagram of the GPU architecture when it comes to memory. On the GPUs, we usually have a big chunk of memory called global memory, sometimes referred to VRAM. And then there's a level of cache, right? And then we have a set of what is called SMs. SMs in the NVIDIA terminology means streaming multiprocessor. And it's kind of, if you want to map it to the CPU, will be equivalent to a core, CPU core. And within the SM, we have a level of L1 cache, and we have a level of shared memory. We also have a set of registers files, and in there are also the functional units to be able to dispatch to run the application. Why I'm telling you this? Because in HAT, we can make use of this hierarchy. Models like OpenCL or CUDA or OneAPI allow us to send data. When you send data to the GPU, it's placed on the GPU global memory, right? So when I talked before about F32 array using Panama, when that array is sent to the GPU, it's sent to this area. And on the GPUs, when it comes to CUDA or OpenCL or One API, these systems, you can also program you can also place your data in L1 cache, close to L1 cache. It's called the shared memory. It's a scratchpad memory that you could use, right? And in wherever you put in there, it's never going to be escaped from that device, right? But it's fast. And if for many applications you want to use that memory. So in HAT, you can also use it. There's also another special region called constant memory. If your data is read-only and you're never gonna change it because it's read-only, you can place it in this area, right? In HAT right now, we can place it in global memory and shared memory. And to differentiate, we have created the concept of mappable iFace. So you have your interface to create your own types, and you stem from a mappable iFace interface. And that means that you kick in the logic to send the data to global memory. And the non-mappable iFace, you kick in logic to send the data to either shared memory or private memory. It depends on what you want to do. Okay, so enough talk. I'm gonna show you now a demo. I'm gonna show you now the flash attention. Not sure if you're familiar with these type of algorithms. So in LLMs, there's a big chunk called self-attention, okay? And flash attention is an optimization for self-attention. Flash attention is mainly targeting GPUs and is making use of tiling and shared memory to process faster and use less memory, and fusion of operations. So we can do the MACMUL and the softmax in the same kernel, right? So I'm gonna jump to the terminal. So I'm gonna run just Java. I'm gonna enable the HAT commands. I'm gonna say use the OpenCL backend. I'm running on a Apple Silicon, so to run on the GPU, I need to enable the OpenCL backend. And I'm gonna run the example of flash attention. Oh, sorry for that. And I specify a context size. That's the LLM context size, okay? Of 2048 elements. I'm gonna run each version. I'm gonna run different versions, each of them 10 times, okay? I'm gonna run the Java application, so the Java sequential one, then the parallel stream version, then the GPU version with HAT, but self-attention, no optimizations in it. And then I'm gonna run self-attention, expressed with HAT, in F32 bits, so floating point of 32 bits, and then flash attention as well with FP16, so using 16 bits floating point, right? So let's run it. So as you can see, the Java sequential takes around 600 milliseconds, then the parallel stream's a bit faster, then the flash attention over here, it takes 12 milliseconds, and the flash attention with 16 bits is less than 10 milliseconds. So end to end, we can run on the GPUs around 60 times faster than Java sequential. And if we compare with parallel streams, it's around 5 times faster, right? But you don't have to, believe me. Let's dive in a bit in this application and see what's going on. So in HAT, we can enable this flag, show code. And when it comes to the GPU, it will spit the generated code that we use with core reflection, right? We generate using core reflection. And as you can see here, for example, for FP16, this is the equivalent OpenCL code that is automatically generated, okay, for us. So you don't have to write this code. It's, as you can see, it's extremely low level, and I presume many Java developers don't want to go there. But let's enable also another flag called info, and this gives us the information about which device, which accelerator was used, right? So I'm gonna rerun the application again, and wherever we kick in the accelerated code with HAT, it's gonna give us the information about the device. So here it's telling us that it's using the GPU from Apple, right? From this laptop, which is great. Okay.
Activity monitor.
Sorry?
Activity monitor.
I don't get the.
Activity monitor will run the program. Activity monitor.
Activity monitor. In real time, no, we don't have that at the moment, but we could extend it. Yes, yeah. No. Right, so let's look at what's going on under the hat now. And what I'm going to talk about is how we use core reflection and dialects to be able to process these type of applications. So in hat, we have the concept of dialect. Dialect means a domain-specific code model, if you like, for targeting, well, in this case, hardware accelerators. And we have a dialect based on MLIR. In this case, we're actually heavily influenced by MLIR. They also have a GPU dialect. And in the dialect, we can expand the basic code model that core reflection gives us with GPU thread accesses, GPU barriers, for example. We can define in the dialect the memory regions that are used, if it's shared memory, if it's private memory. We can define in the dialect the special types, for example, FP16, for floating point of 16 bits, or vector operations, and so on and so forth. So what we are working on is towards the definition of this dialect. Hopefully, the toolkit will have the dialect finalized that we can give to developers in order to expand with new backends. So you want a new backend, this is the dialect that you want to expand, right? Extend. Right, so with the dialect, this is the internal process. So on the top, we have the Java application written with hat, and this application is using local indexes, for example. It's called KC, so kernel context.liy is the local index in the y dimension, and lsx is the local index in the x dimension. And this is just, I think, this snippet from the matrix multiply application. And then on the left side, what we see is the code model without any dialectification, if you like, right? So it's just the code model that we see from core reflection. And all these fields, okay, kc.liy, lsx, etc., we see as a load fields in the code model. Then we have a set of transformations. We call it hat dialectify process, in which we, step by step, okay, introduce operations for the dialect. My colleague Ruby talked about array views, where we have, as I mentioned, thread selection, barriers, math intrinsics, vector operations, vector lanes, and so on and so forth. And at the end of the process, we have the code model, okay, in the hat dialect format. For example, the thread index, the local index, we see a dialect operation to access the local index. And from there, we know how to generate code efficiently. So what's the value of hat for Java developers? What are we offering here? Well, hopefully, a pluggable system to target different accelerators. So we want to come up with this toolkit is essentially the set of tools that you need to override and you need to extend to have your own backend, right? The second thing is an extensible type system that helps developers to exploit a memory hierarchy of your accelerator. I mentioned briefly shared memory, global memory, and constant memory, and those are pretty common on these accelerators, but you might have also other type of memory regions that you want to exploit. And through the interfaces with mappable phase, I phase, and non-mappable I phase, that's a way to get there. And last but not least, we want to give developers an extensible code model, this dialect that I was talking about, that hopefully developers can get and extend to run on other hardware, like a tensor unit or RISC-V accelerator, and so on and so forth. So hopefully this gives value to the developers, not just the hat ecosystem, but also an extensible platform that developers can use. Okay, so let me switch now to two use cases. I briefly mentioned, I'm gonna dive in now. One of the key strengths of hat is that allows developers to express, to compose your own data types, right? And this is a key differentiator to other projects. So in this case, in this study, what we wanted to do is to analyze, is this abstraction give us any penalty when it comes to performance, or I can run at the same speed, right? And I analyze this in the context of the DFT application. Not sure if you know the DFT, a discrete Fourier transform. Basically, this application is heavy compute, and it's using in the core complex numbers. Complex numbers are like a tuple of numbers, if you like, of real floating point number and imaginary floating point number, right? So if HAT doesn't offer you a way to compose types, what you have to do is to define, using the pre-built types, right, probably with arrays, just having a separate array for each element of your data structure. That's on the right-hand side. And on the left-hand side is the complex array that we create ourselves, right? So again, the goal is to analyze if this representation gives us the same speed up or not, and why. So I run this in the A10 GPU from OCI, and here the x-axis shows input size, the y-axis shows performance speed up against Java parallel streams. And these are the two versions, the HAT using user-defined types, and then they have what they call decompose, essentially using the plain arrays that HAT gives you. And as you can see, there's no difference between these two. You can run at the same speed, which is great, meaning that we are sending and receiving exactly the same amount of data, which is expected, right? By the way, this is end-to-end, so it means data send, computation, and data receive, right? We dive in, and we also analyze just the kernel time, meaning just the function that runs on the GPU. We profile the function that runs on the GPU. And we saw an interesting result. So we detect that for small and medium data sizes, the performance is practically identical. And for large data sizes, the difference was around 1%, favoring the one that we call decompose, right? Rather than the data structure that we create. Why is that? Well, we analyze it then with the CUDA profiler. It's called the NCU. That's another nice thing, that because we generate CUDA, we can also use the NVIDIA tooling to do the debugging and profiling, right? This is a screenshot from NCU. And in here, don't worry about the details. What makes the difference is the line I highlight here, which is doing a load from global memory into a pointer here. And that tiny thing is 0.7% of difference. When you have a very large input size, that makes a difference. If we do, in real numbers, like millisecond numbers, what's the difference? We are talking about half millisecond difference here, right? It could be negligible, but yeah, it depends on your use case, right? If your use case, that millisecond counts, then we need to address this. Good news is that by using core reflection as well, we can transform this code. Instead of storing that pointer in global memory, we could use, for example, to store in private memory or shared memory. We haven't done it yet. We have the profiler now. It's something that we could expand in the future. Right, so, but how far can we go? And this is the fun case study here. So we did the following experiment. Using all these concepts here, the ability to explore shared memory, private memory, loop tiling, the ability to have FP16, for example, the ability to express vector operations, and so on, we wanted to analyze how far are we compared to a native library. So we analyze in the context of matrix multiplication, how far are we compared to cuBLAS, right? cuBLAS, I'm not sure if you know this library. It's a linear algebra library written by NVIDIA. It could be considered the fastest. There are ways to get faster, but it could be considered the fastest implementation out there, which is quite good. And why do we choose this application? Well, as you might know, the matrix multiply is heavily used in LLMs, for example, in inference, in training, etc. So it will be good to have this exercise and see how far are we. So this is the code expressed in Java, and what we do is to adapt it using all these constructs with HAT and analyze the performance. In fact, I wrote an article, I think 2 months ago. And in that article, if you like this topic, I highly recommend it because it explains step by step the optimization, why we did optimization, and then highlight the profiler information for that optimization and measure it against CUDA, right? So step by step explain it. Here, in the interest of time, I'm gonna do a summary of this study. So what do we get? Here is a performance plot. I'm gonna explain what this means, okay? So the x-axis shows different versions. The first one is just Java sequential. The last one is native CUDA C++. In between is everything written in hat with different optimizations enabled. The y-axis shows performance, measuring in flops per second. So the higher, the better. So as we can see, the CPU version, the parallel stream version, takes around 7 gigaflops per second. And then what we do was a direct port from that application using hat in 1D range. Remember that ranges that we have? In 1D range. And the performance is around 22 gigaflops per second. But matrix multiply, you can express it in 2D range. And that gives us 200 gigaflops per second performance, a bit higher. And then we did an optimization. We swap indexes between X and Y. So it's kind of a lubricant change, if you like, to improve global memory coalesce accesses. And that gives us almost 1 teraflop of performance. This is written in Java, okay, with hat. Next one, we did optimization using shared memory and loop tiling. And that gives us a speed of around 1.3 teraflops per second. The next one, we did a step further. It was getting more complex, okay? But the idea was the following. With shared memory and loop tiling, you copy your arrays from global memory to share, you do the computation in shared memory, and then you copy the results back to global memory. The next step is what we call 2D with shared memory and register tiling, which is the next level, exploiting the next level in memory hierarchy, if you like. So from global to share, from share to private, we compute the MMA matrix multiply accumulate in private, and then the results back to global memory. And that gives us 5.7 teraflop of performance, right? Then here we have a few variations. We introduced vector types. In this case, we didn't get anything from there. We have other problems to fix in that kernel. And then we did another experiment introducing FP16, so floating point of 16 bits. Just to be clear, if we are running everything with FP32, the comparison should be FP32. But because LLMs allow us to quantize this, we did this exercise. And this gives us access to 7.6 teraflops. And the CUDA, which is using FP32, runs with 8.9 teraflops. Now, we run this with NVIDIA NCU profiler. And this is an extremely good tool if you want to compare different versions. But what they do is to lock the frequency of the GPU and flush the caches every time in order to measure properly. But what if we don't do that? We use instead the CUDA event, so we don't flush the caches, we don't set up the frequency. What we get is a bit high performance. So using the same set of experiments, we go from 7 gigaflops per second on the CPU up to 14 teraflops on the GPU. Again, the real comparison should be the blue one with the last one. So it's 10 teraflops versus 12.7 teraflops because these two uses FP32. But it's great. So it's written in Java. It's low level, but it's written in Java. Okay, it's really good. And can we do better? Yes, I believe so. So yeah. So the last experiment we did was to scale this problem to run with larger data sizes. The previous graph was locked in 1K by 1K matrix size. And we also did the analysis for larger matrix sizes. And we see a similar trend. Essentially, a hat performs around 60% of CUDA, being honest. But we haven't introduced yet explicit tensor operations or warp operations that CUDA does. And I have the feeling that with code reflection, it will be easier to get there. So to finalize, I'm going to jump directly to the conclusions here. I show you how we could run Java applications to exploit GPUs and hardware accelerators. I show you the software stack involved, and I show you how HAT can fit in the whole Java ecosystem. And I show you 2 use cases, one illustrating the cost of data abstractions, and how far can we go through the matrix multiplication. So hopefully, through this exercise, we are more convinced about this technology, and we are looking for feedback. So if you have feedback, comments, suggestions, we hear you. And with that, I conclude my presentation. So really, thank you very much.